This is a concept for vision. This is an attempt to summarize the longer video and the 6 smaller videos into something more concise, and to give some rules for how the system is perceived to work. So in summary, the entire concept could be summarized that we see the world by angular size, and the smallest observable angle becomes the vanishing point or line within our vision. And we can break that down into 3 parts. So the first part is that things get smaller with distance. The second part is that small things disappear. And the third part is combining the two, that small things disappear with distance, secondary to a few things that are expansions upon that concept. So the first being that the small things disappear with distance secondary to the compression rate within a given field of view. And we will break that down into the vanishing point and the concept of a setting object. Part 2, small things disappear with distance secondary to small obstructions within perspective due to the ascent rate within perspective, and we will cover that. And the third thing is that small things disappear with distance secondary to upward refraction of light, the inferior mirage effect, compression expansion effects, and we will give a formula for possible standard refraction. These first 4 slides are just meant to be summary slides of the entire presentation. And so if you'd like to screenshot them for future reference, you can. I'm not going to go through these right now because I'm going to go through them throughout the presentation. But these are the summary slides, so feel free to screenshot and check those out later. This is the first slide. This is the second slide. Third slide. And the fourth slide. So let's get to the argument. This is again a concept for vision, and we'll cover these 3 aspects and in greater detail here. So the first part is that things get smaller with distance, and I'm not going to get into that too much on this particular video because we've covered that in several videos before. But just to summarize the effect, if an object is greater than 2 focal lengths away, 2 rays diverge from the object and travel across focal points in front and behind a convex lens, intersecting at a variable distance between focal points or focal lengths f1 to f2 behind the lens. We've diagrammed that below. They project an inverted image on a sensor such that in the absence of refraction, doubling the distance to the object reduces the image size by 50%, or what we've talked about before, h1 over h2 for 2 differing heights gives us 2 differing distance in the relationship of d2 over d1, where h equals height and d equals distance. So again, if you double the distance to an object, its size reduces by 1/2. And again, 2 rays are necessary to create an image. A single ray does not create an image. In other words, we see the world in angular size. The second part is that small things disappear. And again, we've covered this in the previous video, and this is where we get into the basics of the diffraction limit. And so in order for an object to create an image, it must be larger than a certain size, a certain angular resolution limit of the to the observer, such that the angle it creates between those focal lengths, f1 to f2, is larger than a certain angle, theta in radians, equal to 1.22 times the wavelength of light divided by the diameter of the aperture. So in general, theta can be assumed to be 1 arc minute or 0.02 degrees. To expand on that concept a bit, focal length can be considered for the resolution of objects in nearby distances, but it appears from just personal observation of footage that I've been able to look at that beyond about a 15 to 17 mile distance, even under the best circumstances and best conditions, where water temperature and air temperature are roughly the same, most camera systems revert to 1 arc minute resolutions, and that is how we see the world with distance. So again, the horizon begins to get brought inward and met at that point, at least within that lower compressed field, and the angular resolution limit increases with distance from that point on, and the resolution worsens. So just to briefly describe the diagram here, well, again, we have our tree, we have the top and bottom of our tree with various heights, sending off rays of reflected light to the observer through a convex lens, creating different angles. The angle of light that is created on the back of the sensor gets smaller and smaller with height, and at a certain point, the two diffraction patterns of that light that is being scattered through the aperture reaches a point where you cannot resolve the distinctness or the differences between the two rays, and at that point the image is lost because we need two rays to create an image, to create context for an image, and if we don't have that context, we do not create an image. And so that point again is theta in radians equal to 1.22 lambda divided by d, the aperture. And then we noted again that there are differing ways to produce this angle, and under certain circumstances the angle can be extremely low given the right conditions, and we can resolve great distances and small amounts of information to great detail. And so resolution can also be calculated based on the brightness and the f-stop and any number of ways. It just so happens that theta in radians with the Rayleigh criteria essentially is the predominant way to describe the phenomenon. But resolution can be calculated as theta in radians equal to 2.44 times the wavelength of light times the f-stop. Again, until about 15 to 17 miles, where it appears that the horizon is brought inward at 1 arc minute, at least for the P1000 under ideal conditions. And again, that is Red Pill Philosophy's footage, and I encourage you to watch part 4 of the video series that I put out in order to describe some of those images as they relate to angular resolution. And what we observed within his footage was that there was no loss at 14 miles. The expected loss was 26 feet. There was 30 feet of loss at 17 miles. We expected 31. And then there was 35 feet lost at 19 miles, and we expected 35. So the no loss in the earlier footage, again, was due to the awesome conditions under which he was filming it. So again, subscribe to his channel. He has great footage, and I believe this one was taken in early January of 2019. So throughout, I'm going to try to periodically recap what we've covered so that we can stay within the outline. So right now we are at that we've covered things get smaller with distance. Again, you can refer to roughly part 1 of the video series if you would like to get into that a little bit more. Small things disappear. That is covered in parts 3 mainly within the video series, and now we're going to get into small things disappearing with distance, secondary to various concepts. So the first one is that small things disappear secondary to the compression rate within a given field of view, and the ability to make that angle smaller with which we see the world. So the first concept within that compression rate is going to be the vanishing point. So again, the vanishing point is defined at eye level as the furthest observable distance where the visual field appears to converge within perspective. There exists like a differential compression rate within fields of vision such that altering your observer position to a tangible surface alters the compression rate at which that surface is observed. So a reduction in height will compress more of the visual floor within that lower 50% of your vision. Alternatively, a gain in height will decompress more of that floor within that lower 50% of your vision. And we will show some examples of how that works. But the objects themselves within the visual field do not visibly compress because the distance is held constant to them. But the rate at which a moving object approaches the vanishing line or point is altered because of transversal line compression if we alter our height. And the rate at which the object approaches the vanishing line occurs at a faster rate. So if I lower my height down to the floor, the horizon line is still at the midpoint of vision, but the rate at which an object approaches that line is fairly quick because that line is now closer to the observer. So we will show some examples of how that works within the concept. And these pictures again are just showing in the upper left that again, if I lower my eye height down, I'm just compressing those transversal lines, placing more information within a smaller reference frame, and lowering my eye height with respect to the distant object, in this case the gray box. And the rate at which that gray box were to approach that purple line, which is the eye line, occurs at a faster clip. So for the most part, please refer to part 2 for the explanations on some of these issues. The upper right photo is just, or diagram is just showing that the compression of those lower transversal lines occurs at a certain pace, but it pairs up to the expansion of the upper transversal line. So if I compress my lower visual field to a floor, I'm expanding the upper visual field to the ceiling. And that makes implicit sense to us. We see more of the ceiling when we get lower to the floor, and we see less of the floor. And this occurs in pairs. So the orthogonal lines pair to one another within a floor such that as I compress one, I expand the other. The lower photo or diagrams are just showing how perspective occurs when we rotate the walls away from us and we come to a horizon or horizontal vanishing line. So on the left we have ourselves within a hallway, and the left wall is being rotated away from us, pivoting off of the distant vanishing point. And as that continues to rotate away from us, eventually we will be left with a horizontal vanishing line across our vision with no walls present. And if we rotate then that ceiling away from us, we are left with essentially what we view outdoors, which is a compressed lower visual field and the absence of tangible objects such as walls or a ceiling compressing the left and right and upper visual fields. So here's some examples of how this works within vision. What I'm saying here is within perspective, the ascent rate of the objects changes such that they approach the horizon line very quickly with their lower height. So I'm just in a hallway and I have a light about at the end of the hallway. This is about 450 feet away, give or take. And I am lowering my height down, and at a certain point the light disappears completely from vision several inches off the ground. And you can see if you draw the orthogonal lines within the hallway based on the corner of the hallways, they approach a horizontal vanishing line. So these red lines here are at the corners of where the floor meets the wall on the left and right side. And as I lower my eye height downward, down to the floor, those corners starts to approach the horizontal vanishing line. And again, you can represent that with a perspective diagram, which is in the middle picture. So as I am lowering my eye height and I have extrapolated like some buildings, let's call them these rainbow colored buildings in a row. As I lower my eye height down, I get to the point where the red lines have approached the purple line, which is that horizontal vanishing line. And I am still viewing, however, that lower floor, that 50% of vision is still taking up that small sliver of information. So we'll cover this more in detail as we go. So that's the vanishing point, and we'll cover that as we go as well. So if you didn't catch all of it, it will hopefully become more apparent. But the second aspect is setting objects. So again, we are at small things disappearing with distance secondary to the compression rate within a given field of view. So this is how a setting object occurs. So with the loss of height, the eye line is brought lower within the object being viewed, just like how we brought our eye line lower within that gray box shown earlier in the perspective view. We're just bringing our eye height down with respect to an object being viewed. So and compressing that lower visual field. So given a higher compression rate within the lower field of view, the lower the observer position relative to the object height, the more the object will set with distance. If that object moves away from you, the more of it will set. Similarly, given the higher observer position relative to the object, the less it will set, and the more it will disappear as a whole. So the first part of this is that if the compression rate along a tangible surface, floor, ceiling, or wall, is equal, and the observer is directly in the center, the vanishing point represents a point source of light radiating equally toward the observer from the furthest distance away. This point source represents a non-rendered circle with a diameter of 2 theta. In other words, this is the angle, smallest angle at which any information can be received by the observer. And it is not rendered within vision, it is rendered as a single point. It has a diameter of 2 theta. Objects smaller than the radius of theta centered on the eyeline of the observer are therefore not observed, and the observer interprets this region as a point. If any object is within a given field of view without reference to the vanishing point, again, so you're looking maybe upward or to the left or to the right of you, and you're looking at any object, let's say on the wall or on the ceiling, its disappearance rate will occur at the angular resolution limit theta. In other words, regardless of the vanishing point, any object within the field of view will not be rendered as an image to the observer once the height of it is equal to the distance times the tangent of theta. And we went over that formula in, I believe, part 3 of the series. But remember that the smallest observable object can be summarized in the formula h equals d tan theta, where again theta is the angular resolution limit of the observer, which can commonly be taken as 1 arc minute or 0.02 degrees. Within the diagrams here, we are again showing that we are within a hallway that has equal compression between the floor, the ceiling, and the walls, and the observer eye position is directly in the middle of the hallway. And so within 1 point perspective, we would view the hallway a certain way. And in the orthographic view, if we were to rotate to a side view, we would be viewing angles down or extending away to us from a distant point of theta above the eye line and theta below, such that the radius of that circle could be derived as theta. And so within this point of view, we would note that the height is inversely proportional to the distance for any particular object, or summarized h1 over h2 equals d2 over d1. On the diagram on the right, again, any object less than theta is not observed regardless of where it is in the field of view, and regardless of the compression rate where it is located. So objects of size h can be determined by h equals d tan theta. That's what we discussed already. And again, I'm trying to illustrate for you kind of how the vanishing point appears to someone. So if I were to, say, look at a 6-foot person walking away from me who is carrying a 6-foot stack of balloons at 1 arc minute of resolution, I would watch that person get smaller with distance, and the balloons get smaller with distance if we had a ceiling in this case. So we're in a hallway, right? This is the example where we are in a hallway where we have walls, ceilings, and floors. And if I were to have a person in that hallway walk straight away from me, and they are 12 foot high with their balloons total, 6 feet of balloons, 6-foot person, then it would disappear at 3 miles because the lower aspect of vision will disappear at theta, which is 6 foot at 3 miles, and the upper visual field will also have the information disappear at 3 miles. So both the balloons and the person disappear as a single point at a distance of 3 miles. And again, if we were to look at these balloons or this person any point within any visual field, and for whatever reason those balloons either got too small to see or that person was too far or too small to see, it would occur prior to a vanishing point or line at whatever distance that person or balloon became that size. So hopefully that makes sense. Again, the the smallest point of light that is rendered to an observer is the vanishing point, and that is the furthest point that a person can see. But objects within any given field of view can be smaller than that point, such as a bug or a hair on the floor, and those items will disappear prior to a vanishing point. So to continue this, that was equal compression. So we're in a hallway again where the floor and the ceiling and the walls are equal distant from the observer. And now we're going to lower ourselves down to the floor or raise ourselves up towards the ceiling. And we're going to now have a differential compression within that field of view. So if the compression rate along the floor, ceiling, or wall is differential, and the resolution limit is met across any aspect of the visual field prior to another, a vanishing line is created such that the objects opposite this line will set into it at a faster rate with distance. So when the observer reduces their distance to a tangible surface, the vanishing point draws closer and merges with the nearby vanishing line with an angle of theta. Objects beyond this line set with distance into a horizon gap, and I'll explain this in detail as we go. But essentially, if you are in this same hallway and I get now low to the floor, I am now compressing more information within that lower 50% of vision. And when I do so, theta is brought nearer to me. Meanwhile, I'm seeing more of the ceiling in this case, and theta is actually pushed further away from me. And so what's created between the two is a horizon gap. And the same effect occurs within this same hallway if I push myself high towards the ceiling. And now I am viewing less of the ceiling within the upper 50% of vision, and I'm viewing more of the floor within the lower 50% of vision, and the same horizon gap occurs, just inverted. So if this doesn't make sense now, hopefully it makes sense with time. So I'm going to explain this horizon gap with some practical examples. So what I did was I took this long, roughly 450 foot long hallway, and I placed golf balls along the visual field within the hallway at 10-foot intervals. So golf balls were placed directly below lights that were also at 10-foot intervals, so that I could correlate the lower visual field to the upper visual field. So the first golf ball that is visible was placed roughly 20 feet away from the observer position. And then after that point, they were spaced 10 feet apart, and they correspond to the lights above them, which are also spaced at 10 feet apart. So again, each light is 10 feet apart, and each ball is 10 feet apart. And there are 12 balls total within this field of view, and I placed a light at the end of the last ball. The balls start 20 feet away. There is about 130 feet to the last ball within this frame. And I did pictures across the wall that was behind me at 1 foot intervals. It's an 8-foot wall, roughly 8 feet. And so I took pictures at the very top at 8 feet. I was just shy of it by maybe an inch or so, but I couldn't reach up this high. But it's almost to the top at 8 feet. Then I took one at 7 feet, 6 feet, 5, 4, 3, 2, 1, and down to 0 feet, which came out to roughly 1 centimeter off the ground. And then we compare what we see within this observation. So the top left photo is going to be where the upper visual field is at roughly a couple inches, and the lower visual field is at roughly 8 feet or so, or 7 feet, and about 10 inches or 11 inches. The next picture is going to be where the upper visual field is at a 7 foot, or excuse me, the upper visual field is at a 1 foot height from the ceiling, and the lower visual field is 7 feet, or roughly a 7 foot observer height. And then as we go down, we get to a 6 foot observer height, then a 5 foot, 4 foot, 3 foot, 2 foot, and so forth. And so we can then draw lines on where the lights and where the ball the corresponding paired ball is located. So I color coded them so that where the ball and the light appear to be directly beneath one another is a certain color. So the first ball and light are going to be red, the next one's green, and the next one's yellow, and then pink, and then brown and orange, and so forth. And so I did that for 12 balls. So each of the colors goes from um, uh, uh, red to green to yellow, pink, brown, and orange, and then that cycle repeats itself one more time for a total of 12 color pairs. So when I map this out for the upper and lower visual fields, and you can replace the red line, if you wish, the top red line to the bottom red line, you could say that's a building, right? And then the next building would be 10 feet away, would be the green upper line to the green lower line, and so forth. And you could stratify that if you wanted to, but we'll just look at it this way for now. Keeping in mind that, again, 50% of your vision is going to be the upper field, regardless of the height to which you are ascribing your field, and the lower 50% is going to be the lower aspect of vision, regardless of your height. So we can draw these lines and then we can take them out of the photo to kind of get a better idea about how things are compressing, and you can make your own determination for the rate at which this is occurring. And I will show you how one can determine what this rate is. But you can see how we are compressing a lot more information when we have a 1 foot observer height than when we have a 7 foot observer height. But again, it's still taking up 50% of vision. And so I can kind of extend these lines out to show you this rate. This is an exponential rate. We'll show you the formula for what this rate is, but for now, just realize it's exponential, right? It's not a linear rate with regard to distance. We know the distance is being held constant, but the rate at which the size reduces is exponential. But what's not realized is that the distance is also exponentially compressing away from us. So this is, we'll get into this, but this maps out along a log-log or exponential plot, not a exponential and linear plot, or what's called a semi-log plot. And we'll kind of cover that later. But for now, just realize that both distance and height exponentially compress. And when you compare the two, you get a linear world. And if you were to only take into consideration one of those things compressing exponentially and the other linearly, you would erroneously extrapolate a curve, and we will get into that later. So this is a bit more analysis of how we can apply the formula of H1 over H2 equal to D2 over D1, or essentially how things get smaller with distance. If we double the distance, we half the size. So when you look at a photograph in perspective, you can take whatever distance you have for the first 50% of vision, and you can keep having it, and you will double the amount of information that is in each subsequent half. So if I am looking at the floor in this case from a 1 foot observer height, which is the picture in the middle where there's the 7 foot on top and the 1 foot on the bottom, I can count the tiles within this photo, and I can see that I'm roughly at 1.5 tiles within the lower 1/4 of the total image, or the lower 50% of the lower half of the image. Again, my lower visual field. And now if I were to half that distance again, so now I've half the distance of that first of the red line, and I've halved it into the orange line, I have to double the amount of information that is contained within that block of vision, essentially. So I go from 1.5 feet to 3 feet, and you can see that that's roughly the amount of tiles that are there. And then I go from 3 feet, and I do this same process again, and I compress to 4x, and I get to 6 feet, and then I go to 12 feet, and this keeps compressing and compressing and compressing until the vanishing line. The same thing occurs, or remember we said that orthogonal lines occur in pairs, and so as I compressed my lower visual field to the 1 foot observer height, the upper visual field expanded to the 7 foot observer height, essentially, just inverted. And so I now have much more information contained within that upper 1/4 of the total image, or the upper 50% of the upper half of vision. And so since I had 1.5 feet on the lower 1/4 of the image, I now have 11 feet in the upper 1/4. And so if I were to double that, and you can tell that's how many I have. You can count the number of square feet, and you can see that it is roughly 11 feet. Again, each light itself is about 2 square feet. And so we have roughly about 5.5 square feet worth of information. Or sorry, 5.5 rectangles, which comes out to about 11 feet. So now if I continue that process onward, the next iteration at 2x compression is going to be 22 feet. At 4x it's going to be 44, then 88, and so forth. And so if I take that 1 foot observer height and I just invert it and flip it upside down, so that now I'm at a 7 foot observer height and I'm 1 foot to the ceiling, I just reverse all those numbers and the same effect occurs, and you can count almost the exact same amount of information. So in the lower aspect of vision, I'm now counting roughly 11 tiles, and then I'm counting 22, and then I go to 44 and 88, and it works just in reverse. So hopefully that makes sense. This is how we compress perspective within our visual field. This is how perspective compresses information. So you can map out a grid, and we can extrapolate what the number of feet are if we continue this process outward or away from us. So hopefully that makes sense. It's important. I hope you can digest that, because it's extremely important to realize how this works in order for you to continue on. So at the 8x distance, we'll say, which is that green half division, I can only resolve 12 feet below the eye line and 88 feet above the eye line, right? I'm at 12 foot below, and I'm at 88 feet above at that same 8x compression rate. This is because distance is proportional to observer height, as O, again, that's the observer height, O1 over O2 is equal to D1 over D2. So I double my height and I double the distance I can see. And again, that's in part 3, I believe, of the video series. And the object size that I'm looking at is inversely proportional to the distance, or H1 over H2 equals D2 over D1. So the observer heights are 7 foot divided by 1 foot equal to 7. So distance relationships will occur at this same ratio. So you'll notice in the columns on the table that 11 divided by 1.5 is going to be roughly 7, 33 divided by 4.5 is going to be roughly 7, 77 divided by 10.5 is going to be roughly 7, and that ratio will remain constant throughout. So, so we can extrapolate this table out, and we see that if we carry it forward at about 819x compression, we've reached roughly what the angular resolution limit would be for a 1 arc minute resolution, which is roughly 2,764 feet away from us. So if I take d equals observer height divided by tan theta and find out what the number is, my vanishing line should be roughly 2,865 feet away. And if I just take a picture of myself 1 foot off the floor, or where O is equal to 1 foot, I can extrapolate just from the image that it's roughly the same at 2,764 feet away. So we can zoom in on what 819x compression would really look like but it's incredibly small. And so if you picture that from 8x to 16x, we compressed 1/2, and then from 16x to 32x, we compressed another half and another half and another half, and we kept halving it. We get all the way to 18 or 819x before we even meet our horizon line. And so I can do this for not just 7 foot and 1 foot, but we can compare 3 feet and 5 feet, and we will get the same phenomenon. So as when I was 1 foot above the ground, I'm now 3 feet above the ground. And where I used to have 1.5 feet compressed within that lower 1/4 of the image, I've now compressed 5 feet. And conversely, when I raise myself up to 5 foot observer, I've now compressed 8 feet into the lower 1/4 of vision. And we can just extrapolate this forward and get the same phenomenon. So at 819x roughly for this particular camera, which is an iPhone 6s in this case, we reach a point of 1.55 miles. And if I were to calculate what 1 arc minute of resolution would grant me in terms of distance, I would come to 1.63 miles, and they are very similar. So we will carry this forward, and again, keep in mind that the relationship of height and distance is still linear to itself. Even though each one exponentially compresses, the relationship between the two is linear. So the observer heights are now 5 foot and 3 feet, 3 feet for an observer ratio of 1.67, and we see that the distance ratios remain the same at 1.67 roughly. Keep in mind that I am having to average the amount or try to find as much of it as accurate as possible a distance relationship within that lower, the amount of tiles that I'm actually seeing in order to extrapolate that forward. So there is a little bit of an error factor there. But it is roughly the same ratio of 1.67 to 1.8, and it maintains itself throughout as that information compresses off into the distance. So please feel free to take a look at the lights and the balls below and how they relate to one another with these differing heights, and try to come to terms with how this compression occurs with distance within perspective. So now we're going to lower ourselves down to 1 centimeter, and we're going to get a little bit better glimpse of how this 819x compression really looks within vision. So if I lower myself to a 1 centimeter observer height, for one thing, you can see that the corners along the hallway essentially are on a flat line, and that is now my horizon line or horizontal vanishing line. And if I blow up this image and look at where the first ball is, it's actually now very close to that purple line, because we've reduced those transversal lines to such an extent while keeping the lower 50% of vision in relation to the floor. And so the first ball is essentially almost already at the horizon line. And so if I extrapolate these numbers forward, I see that I have 0.05 and then 0.105 and so forth along the lower aspect of vision, and correspondingly above the upper, the more expanded version now at roughly an 8 foot observer height, I am seeing 13 feet followed by 26, 32, or 52, 103, and so on. Every time I half the distance or double the distance, I half the size, right? And so we can just carry that extrapolation forward. And when I do the calculation this way, both for the visual evidence and for deriving theta, I find that the picture compresses at 819x at 97 feet away from me at 1 centimeter height off the ground, and that if I take 1 centimeter off the ground divided by the tangent of theta, I arrive at 95 feet. So they're within 2 feet of one another. If I expand the center of the picture to show you what 819x compression looks like, I can see that between the blue and the purple line, remember that blue line was 16x compression. If I half that distance, I get 32x. And then if I half that distance, I get 64. And then if I half it, I get 128, and then 256, and then 512. And then you can see how we've already approached the point where this is essentially 1 or 2 pixels within the frame. It is very difficult to resolve that information. But we're going to go ahead and go another uh, line to 819x at least. So what this means is that any golf balls beyond 90 to 100 feet, or roughly 95 feet, will begin to set within vision. Okay, they are now within this horizon gap between the ceiling and the floor. And I may believe that within perspective, the eye line intersects 1 centimeter off the ground along that distant wall more than 400 feet away. In other words, that I am viewing the all reference points with 1 centimeter off the ground as far as I can see. The problem is I cannot see 1 centimeter off the ground 400 feet away. The actual point where 1 centimeter off the ground would intersect a wall would be at 95 feet. So if, let's say, this hallway were, instead of 400 feet, it were 95 feet, well then yes, I would see 1 centimeter off the ground in that case. But this hallway is now 400 feet in length, and I do not see that far. So again, after that point, the lower aspect of your vision ceases, and the objects, i.e. the golf balls in this case, will set with distance. And so I've kind of outlined and blown up that picture one more time for you to see what's going on. And again, the purple line is roughly that point where those orthogonal lines all become horizontal within the visual field. And so if I look at where the first ball was, we know that it's at 20 feet away. That next yellow line is 30 feet, and then 40 feet, 50, 60, 70. And if you just calculate this out, you see where that purple line at 90 to 100 feet roughly corresponds to. And we know that we've extended these balls to 130 feet, but any point after that 95 foot mark, those balls are going to be setting with distance, and we are going to be losing the bottom aspects of those balls. Whereas up to this point, up to that 90 to 100 foot point, again, our distant vanishing point is still above the horizontal vanishing line at 1 centimeter off the ground. Any point beyond that, though, and it begins to set. So hopefully this makes sense. And if it doesn't, stay with me and we will cover this more as we go. So we can extrapolate what is going on with this floor to then say, well, if this phenomenon goes on within this hallway, what happens if I just remove the walls and remove the ceiling, let's say? So now I'm in this same building, and then there's like a tornado or something that comes through, wipes away everything, and I'm left with just a massive expanse of floor. Okay, and so you can either do that conceptually, which is what I provided for you in the diagram for how to rotate a floor away, the walls from the 6-foot observer height, or you can just do it in your head where you were sitting on the floor here at 1 centimeter height, and the whole building gets blown away. Now you're just left with this massive expanse of a long floor. And so if I were to stand up, we wouldn't expect that this visual phenomenon would change with height. In other words, because I have the walls here, I am getting a sense of how the orthogonal lines compress. But if I had no walls and no ceiling and just a massive floor, if I stand up, I would just still see massive floor, but further out and further along, maybe several miles of it. And so, again, our vision doesn't just change because we go outside. The same things that we see indoors occur outside. You just don't, notice it because we tend not to have walls. But it's the same exact phenomenon. So if I just say that I'm going to blow away the walls and the ceiling and look at what I'm left with, I'm now just left with the sky. And I'm 1 centimeter off the ground still, but the ceiling and the walls have been removed, and I'm just in this massive expanse 1 centimeter off the ground. Okay, and now I'm just going to stand up. All right, but I am along, let's say now I'm, instead of along the ground within this building, I'm just very low to the ground in a field, let's say, and then I stand up. The same visual effects, which are these orthogonal lines, kind of, and how they approach the distant vanishing point and vanishing line, are going to be the same. So it's going to look like this, and you're left with a landscape. And this is not curvature. This is not the curvature of Earth that you're looking at as a bulge within your vision. This is just how your vision works. So when raising your height, you resolve more along your lower visual field, just like we showed about with how many feet per aspect of vision we get to see when we raise our height. It has nothing to do with curvature. So if I just take a 6-foot observer height, in this case, with an unknown ceiling height, I don't know the ceiling, but I just know the floor in this case, I can extrapolate how long and or how much information I should be able to resolve within each 50% iteration of the lower visual field. So every time I half the lower visual field, how many feet am I observing? So I first observed 9 feet, then 18, then 36, 72, 144, and that keeps accumulating. So if I sum what I'm seeing within that first iteration as 9 feet, and I'm seeing another 18 feet within the next iteration, my sum is now 27 feet as far as distance away from the observer. And I keep doing that, and what you'll find is that at 819x, for in this particular case, I can see from a 6-foot observer roughly 3 miles away, which again is what we can calculate out with the angular resolution limit for an observer at 1 arc minute. So I'll try to diagram this a little bit differently for you. So returning to our photos, we now see that we do not see as far along the floor as we do along the ceiling if we lower our eye height. So our depiction of the amount of floor or ceiling must change orthographically. So I can't just have a single point now when I change to the side view. So when performed, we see a curvature can be assumed within the horizon gap as the floor shortens. In other words, as those objects start to set within vision because they've gone further than that lower visual field extends, then one could conceivably say, I'm seeing things curve over a distance, but you're not. This is just you've encroached upon that lower visual field's limit of vision. And so I've kind of tried to diagram out for you. This is, again, just crude because it's very difficult to diagram this from a side view. But I've tried to give you a conceptual idea of how this looks and how this horizon gap forms. So as I, in the first case here, I'm at this 8-foot height and I have my eye very close to the ceiling, I'm seeing very little along the ceiling, right? Very short distance along that ceiling. Alternatively, along the floor, which is the red line in this diagram here, I'm seeing a very far distance. I can see a lot of the floor, right? And as I get lower and lower and lower, and I lower my observer height within this hallway, you can see the effect that occurs until I reach that 1 centimeter height, which is that 0-foot mark. And now I see very little along the floor, and I see very far along the ceiling. And when I compress those two within perspective, you can see how these golf balls, which I've diagrammed along the bottom, change in angular size. So as I get lower down, I'm getting closer and closer to that first ball. It's going to get larger and larger and present a larger angle to my eye. But I'm going to be seeing less along the ground. Okay? And alternatively, as I raise my eye height up, I'm getting further and further away from the balls. They get smaller. Their angular size compression rate, however, lessens. They become more stable with distance. So hopefully that makes sense. Maybe spend some time going back over those tables if it's not, it doesn't kind of click, because it can be difficult. So the final thing is, what about the information that I don't see at all that I know is there between the observer and the first pixel within the frame? And this is the vertical field of view. So what is lost in that vertical field of view, and how does it change with height? So the vertical field of view must also be accounted for to gauge a more accurate distance between the observer and the horizon. So from our hallway example, if the horizon is roughly 97 feet away, assuming 1 arc minute, then the lower 50% of the lower visual field is roughly 0.6 inches. So remember how it was 0.05 feet. We just convert that to inches and we get about 0.6 inch. And so I put a ruler just to verify that that is indeed what we see within that lower 1/4 of vision. And I placed a piece of blue paper 1 inch in length across the ruler and put the ruler down where the phone was along that floor. And you can see within this frame that the red line corresponds to where the end of the paper was. And we know that the end of the paper was at 1 inch. And so we can extrapolate from the amount of paper that is visible within the field that roughly 2/3 of the paper is visible, and we're missing about 1/3 of that paper. And so it comes out to roughly 0.6 of an inch and roughly 0.4 of an inch. So we've lost 0.4 of an inch within the vertical field of view of that lower visual field. So I'll just kind of reiterate what I wrote here. We can measure the loss from the vertical field of view with a ruler. If we place the camera at the end of a ruler, we see that 50% mark below the horizon line, again that lower 1/4 of vision, corresponds to a distance of roughly 1 inch as far as this total actual distance away from the camera. We can see 0.6 inch within the picture, leaving 0.4 inch missing within the vertical field of view. And note that the greater the tangible surface, i.e. wall, floor, or ceiling, to the observer, the greater the loss within the field of view. For instance, while we lose 0.4 inch from the lower visual field, we lose 16 feet from the upper field. So again, your camera has a fixed vertical field of view. And so if I am close to the floor, I am resolving or I'm losing less of the floor because I'm closer to it. But if I were to calculate the amount of missing information from the upper field of view, it's much greater because the angle is held constant, but the distance to the ceiling is greater. And so if I extrapolate the vertical field of view to the upper aspect of vision, it comes out to roughly 16 feet. And you can just do that with basic trigonometry using that 65-degree angle. So we'll cover this more here as we go in the next slide. So using a distance of 20 feet to the light or to the ball, we can extrapolate the vertical field of view loss to find for the angle within perspective. So this is how I found for this 65-degree angle. We can solve for the angle as well using the arctan of the field of view loss divided by the height to the obstruction, either the ceiling or the floor. So given this 65 field of view or 65-degree field of view loss for an observer distance to a tangible surface, we can summarize this missing amount as field of view loss equal to 2 times the observer height. So if that seems a little confusing, just stay with me. I will try to go through it. But I don't want to go through it in too much detail because what I've found is that this loss is fairly negligible when we are talking about the distances and what we're observing. But I want to make sure it's here in case this has relevance to someone down the road. So within the table, I'll just try to explain what each of the categories is. The lower visual height just means that what is the lower 50% of vision, the area underneath the purple line, what is that height? And then the area above the purple line is going to be the upper visual height. In other words, the ceiling distance. That's going to be in feet. And then the second column is going to be the lower distance to that first 20-foot ball. In other words, how much within that lower visual field is visible before I see that first ball. And I know that that first ball is 20 feet away. So if I'm at a 8-foot observer height, I only see about 2.5 feet within that lower frame before I see the first ball. Whereas in the when I lower my eye height down, I can see roughly 19.95 feet before that first ball. And so when you do this, you can calculate out the angle using trigonometry. And so what I came to was it averages out to that roughly 65 degree, maybe 63 degree angle between all these various heights. And then when you do the math on this, since tangent of 65 degrees is 2.14, we can derive that essentially the field of view loss within any given, or within at least the iPhone 6s, is roughly equal to 2 times the observer height. And so feel free to look at that in more detail if you'd like. I gave some diagrams up on the upper right to kind of show that if we are have a greater distance to the tangible surface, either the ceiling or the floor, our field of view loss is going to be greater. And that makes sense. So continuing on with this differential compression, and hopefully the horizon gap makes a little bit more sense now. The main thing is that if I lower my eye height to the tangible surface, I bring that lower horizon inward, and the upper horizon moves further out at a further distance. So as we have induced a nearby vanishing line by reducing our distance to the tangible surface, the rate at which a given object within the given the same angular size approaches the vanishing line quickens as the transversal lines compress. So just as that ball reached the purple line very quickly when I had a low height, that's the same phenomenon. So those transversal lines became compressed, and the object reaches the horizon at a very quick rate. When I lower my eye height. So as such, the same object will set into the vanishing line or horizon with further distance more quickly than when the observer's distance to the tangible surface is larger. Meaning, if I were to stand up, that it would take a lot further distance for that object to set. So the disappearance rate of a setting object, or the rate of approach toward the vanishing line or horizon, is determined by observer position. And we can summarize that statement as below with some formulas. So the horizon or vanishing point distance, d observer, is set at the observer height O, such that d equals O divided by tangent theta, where again observer height determines distance that is seen, or O1 over O2 equals D1 over D2. And that's represented in that triangle of similar triangles. I raise my eye height, I look further, because theta is still the vanishing point in the distance, or vanishing line. So that's part A, is how far can I see? All right, that's step one. So I have to know my observer height to know how far I can see. And I would also need to know the resolution limit of the camera that I'm using. In the case of the human eye, we can assume 1 arc minute, but the cameras that are out there have many different angular resolution limits, and depending on the conditions, some can be extremely low, meaning the resolution is great and the distance that you can see is quite far. Part B then, any object within a given field without regard to the vanishing line disappears at the angular resolution limit once its height is equal to the distance that it is away from you times the tangent of the angular resolution limit. And we've covered that with the vanishing point. It's the same phenomenon here when we have a horizon gap as we have with a just single vanishing point. Again, doesn't matter if the object is at the horizon or not. If it's just too small within any given part of the visual field, it's just too small to see. So that's part B. Part C, objects partly within the eye line, i.e. they have parts of them above and below the eye line, and they're moving straight away from you, similar to a car, let's say. They are traveling in both the compressed and expanded fields of view. They disappear at a distance d equal to the observer height divided by tangent theta in the compressed field, that first field, where after that they begin to set. And that distance is then the distance equal to the object height that is still visible once it reaches the horizon line, minus the observer height divided by the tangent of theta. So we'll go through an example here for how that looks. And hopefully the diagram that is shown makes a little bit more sense now just for this clock tower, where again we have induced a nearby horizon by lowering our eye height, and we have created a further horizon by lowering our eye height along the top aspect of the clock tower. So when would an 18-foot clock tower disappear from a 6-foot observer? That's the question. So the horizon distance is d equal to, again, we're just going to use the same rule. So we're going to first set our horizon distance. So the first part is d equal to the observer height divided by tangent theta. So we have distance equal to 6 foot divided by tangent of 0.02 gets us 3 miles. So we're going to be able to see 3 miles along the ground. So the object is within both fields, so the bottom disappears at d equal to observer height divided by tangent theta. So again, the bottom 6 feet of the clock tower is going to disappear at 3 miles. Okay? Now we're left with what's remaining. Once that clock tower gets to the 3 mile mark, we're only going to see the top 12 feet of the tower. So the remaining parts of the clock tower set within the horizon distance at d equal to h minus o divided by tangent theta, or 18 minus 6, which is 12, divided by the tangent of theta, and that's at 6 miles. So for a total distance of 3 plus 6 equal to 9 miles. So this 18-foot clock tower will completely disappear below the purple line 9 miles away. So again, the object still disappears at 2 theta. It's just it occurs at different times. So if I were within a long corridor, an 18-foot tall corridor, and was directly in the middle at 9-foot observer height, this thing would still disappear at 2 theta, which would be at 9 miles in this case. But because I've induced a lower field of view, the lower aspect sets across the horizon gap sooner, and that corresponds to my observer height, and then what's remaining of that clock tower continues to set with distance until it disappears. So again, if I were equidistant within this hallway example, and my observer height was 9 feet, and there was equal compression between the ceiling and the floor, and I had this 18-foot tall object, and it moved away from me, it would disappear as a single point within the vanishing point. But if I lower my eye height within this same corridor and were to watch this object move away with distance, I would see the lower aspect ascend to the purple line at a faster rate because it is nearer. In other words, the lower horizon is nearer, and what's remaining of the clock tower after that point would then set with distance, but the number still comes out to 2 theta. So here's just some other issues that have come up with these pictures and photographs for where one could derive the appearance of curvature, an apparent curvature. But again, it's not curvature, it's just how your vision works. So note how the ascent rate changes between the 1 foot and the 1 centimeter heights. Again, I'm just 1 foot off the floor for the left side, and I'm 1 centimeter off the floor for the right. Notice how that horizon line is breached very quickly at a shorter distance. So again, the golf ball is 20 feet away, it's almost already at that vanishing line. So the horizontal line for the 1 foot height is breached at 2,864 feet if 1 foot off the ground, assuming 1 arc minute, and the transversal line for the first ball is much further away from the horizontal vanishing line with just that 1 foot elevation. So you can see where the start of the red arrow starts. There's quite a big distance that still has to be compressed in order for me to get anywhere near that purple line, because that lower horizon is 2,864 feet away, well beyond the, that's a half mile, right? So that's well beyond how long this corridor is, which is only about 400 feet. Now I go down to 1 centimeter, and the horizon line is breached at 95 feet away. Okay, it doesn't even reach the end of the corridor, which is 400 feet away. So other things to consider here within our long hallway, we see that the floor ascends very quickly, again, within horizon to that horizon line if we lower our eye height, and the ascent rate can be difficult to ascertain, but we can scale the effect down and see what is happening, okay? So when we remove the lines from the photo, so in other words, if I take a, this is just in the bathroom, right? And so if you put the balls along the floor and at a standard rate in a straight line, and then you make sure the floor is level, you can shoot a laser 6 millimeters off the ground, and it's not obstructed, right? But when you look at what this photo appears to be, you can almost get this sense of curvature. What is the ascent rate for these balls? Again, these are just this is just along a short distance, but we can see how they rapidly start to encroach the apparent purple line within this field of view. So I can take those lines and I can pull them out, and we can look at them without the photo backdrop. And that's what I've done with the gray box below. And so you can see how that purple line gets encroached fairly quickly. So when we remove the lines from the photo, we see the transversal lines rapidly approach one another with distance, and the ascent rate rapidly diminishes toward a horizontal vanishing line. So 0.6 inches takes up 25% of the total image. We've already talked about that. And 50% of the lower aspect, okay? At 1 arc minute, this will always represent 0.05% of the total horizon distance. So when we were 1 centimeter off the ground, we know the total distance was about 97 feet. So the lower 1/4 of a total image is only going to correspond to 0.05% of that total horizon distance. In other words, much of the photograph or image is going to be taken up by a very small amount of information. So the balls are in a straight line and the floor is without appreciable obstruction, yet the balls taper and plateau within less than 20 feet, just as we saw with our hallway example. And so if we were to counter this then, what's the corollary to this? So moreover, 86% of the total horizon distance is contained within 0.4% of the lower visual field. So almost all of that 97 feet worth of information is contained within just 0.4% of the lower visual field. So again, that's the point where 256x to 512x to 819x was subtracted away from the total distance of the photograph, from top to bottom. So again, if at 1 arc minute, we assume 1 arc minute of resolution, 86% of the total horizon distance is contained within 0.4% of the lower visual field. And if 1 arc minute, 0.05% of the total horizon distance is contained within 50% of the lower visual field. So again, the main idea here is that very little information is taking up a large amount of space within any given photograph. And that's the main idea here, because the ascent rate can rapidly approach the horizon line. So some more appearance of curvature. You can see that when objects at the same distance are individually mapped and compared, we can extrapolate a curve. So we see that every time we divide the frame by 1/2, we place twice as much information within that reference frame. Remember that h1 over h2 equals d2 over d1. In essence, we're placing more information within less space. If we were to map an individual object within the frame, say an 8-foot tall object moving away at regular 10-foot intervals, its angular size will reduce by 50% once we move two times the actual distance. Okay, again, that's just the same formula. But distance is also exponentially compressing toward the horizon. So if we were to analyze the exponential height changes that we observe orthographically, we would also have to scale the distances exponentially further away. Otherwise, we would erroneously extrapolate a curve. Both distance and height compress exponentially, or restated, both height and distance are inversely proportional to their opposing axis. We can summarize this statement as below. Distance is proportional to 1 over height, and height is proportional to 1 over distance. To put another way, perspective represents our linear world by coupling exponential height change with exponential distance change. If one ignores this effect on distance within a perspective view and then maps a loss rate at regular distance intervals, they would infer an exponential height change across a linear distance and erroneously extrapolate a curved surface. So I hope that makes sense. And if it doesn't for right now, you will see it in a diagram here on the next page. So if we plot exponential information along two axes as a semi-logarithmic plot, meaning it's linear in one dimension and it's logarithmic or exponential in the other, we extrapolate a curve. If plotted as a log-log plot to accurately depict the shape across which information was gathered, we extrapolate a straight line. So again, and this is just getting to how possibly we were put into this position where we believe the surface upon which we stand is a curved surface. So if you were to take any interval, let's say 10 foot markings, any distance away, and then you were to extrapolate how much drop you were experiencing with those 10-foot objects, and then you were to plot them, and you were to say, well, it's every 10 feet, so that should just be every 10 feet on the x-axis. And you were to do it that way and to mark what the height change was, you would be doing a semi-log plot. And so that's represented here with our green man, who is exponential in one axis and linear in the other. And however, when we accurately depict what that actually looks like, because both distance and height reduce within perspective exponentially across a log-log interval, we extrapolate a flat surface. And so I don't want to get into that too much. I have dedicated part 5 of the series to that, discussing how possibly the 8 inches per mile squared formula was derived, as well as the Earth's radius using 2 theta. So, but in essence, if I'm a 6-foot observer and watch a 6-foot person walk away, I can take a picture every 10 yards and see that person's angular size reduce rapidly with the square of the distance away, for instance. But the reason they do so is because distance is also rapidly reducing at the same rate, i.e. exponentially. So if I take the height reduction observations and plot them semi-logarithmically, once again, I would erroneously conclude a surface is curved. So again, please see part 5 for more discussion on that aspect. What I'm showing here in the upper photo is just the linear rate. If you extrapolate the pixel change within that photograph versus the actual distance away, you get a linear relationship. Another aspect here is on the appearance of curvature is, again, you can just do left to right compression within what appears to be a flat surface, and you can extrapolate a curve out of that when we compress it from left to right. That's been discussed in other videos. I won't get into it too much here, but just another tool in the toolbox for how vision really is can be deceiving as far as curved surfaces, because we are looking through a convex lens for almost all observations. And this is just a light disappearing example, again keeping in mind now that you understand this horizon gap phenomenon, that the horizon is brought nearer to me from a point of roughly a half mile at 1 foot off the ground to a point of only less than 100 feet when I get down to 1 centimeter or so. And so in this case, the light is about 450 feet away. You can see it just at the end of that hallway, just down on the lower right aspect of the door. There's a small light there. I'll zoom in on it so you can see how it disappears. Again, so if I were to take those visual fields that we outlined between the light and the golf balls, where the red line, green line, yellow, pink, so on and so forth, that distance away, and if I were to just remove the upper field of vision away from the equation, and now we're just concentrating on what we're compressing within the lower field of vision, you can see how we essentially get down to the point where we're just viewing the purple line. So again, the ascent rate is getting compressed to the point where the 20-foot ball is already at the horizon line, because the horizon line is brought nearer to me. So let's see, we'll watch the video first, and then I'll go ahead and explain some more. There it is, light appearing, and we're going to go down, light disappears, and we keep going down and down a few more inches. Okay, so this light isn't that far away, again 450 feet, but it's beyond the angular resolution limit of the lower visual field, and it sets across this relatively flat surface a few inches off the ground. So one may claim that the surface isn't perfectly flat, and I agree, but then the argument is that objects set across uneven surfaces, not necessarily curvature. The uneven surface could extend for miles in this same exact way and never drop as a curve. The setting phenomenon would still be present, and there would be no evidence of an overall curvature rate. And we'll discuss uneven surfaces and obstructions later on. But note how 100% of the distant wall disappears near the bottom, and not just certain areas of it. In other words, implying the obstruction would have to be evenly spread across the floor for it to just be obstruction and not a angular resolution limit. So for now, realize that objects set with distance and the surface does not have to be curved. So I'll play it one more time, but just watch how the lower aspect of the distant wall of the door appears to set across the entire visual field, not just one or two areas where a floor may be uneven. There it is, light is gone, light appears. So watch the distant wall. Watch how the whole thing seems to set. Now you see much more of it. And it's not just one part of the floor, it's the entire aspect. Evenly. Alright. So again, just to kind of analyze this and put our building example back on to this photograph where the light was, the visual floor comprises several visible tiles, and the iPhone 6s horizon at 24 inches is roughly 1 mile, assuming 1 arc minute, and it's well beyond this 500-foot floor or 450-foot floor, and the light is going to be clearly visible because it's within a much more expanded field of view. Now I'm going to lower my eye height down to just 1 foot, and I'm getting to about half mile away. Okay, but it's still well beyond this 500-foot floor, and the light's going to be visible. Now I'm going to reduce my height even more. Now the visual floor, most of it is just about 8 tiles or so, as far as how many I can count, right? Keep in mind that compression rate when we did the 50% halving. So for the iPhone 6s horizon at 1 centimeter height, we had a 95-foot horizon line, assuming again 1 arc minute or about 95 tiles away. Anything beyond 95 feet will begin to set. So if the floor is 500 feet, we'll lose an additional 1.73 inches, which is 500 feet minus 95 feet. That'd be the horizon gap times the tangent of theta of setting objects by the end of the hallway. So again, that's just how much information would be able to set, which is why it takes about 1.73 inches for us to complete. When we're about 1.73 inches off the ground, we start to lose that light. So note how the red orthogonal lines are nearly horizontal as the horizon. So those corners along where the floor and the walls meet, they're almost completely horizontal with the horizontal vanishing line. But that visible floor still represents 50% of this image. So we can change the backdrop now, but the same effect is going to be observed. The flashlight now becomes a ship, and it disappears bottom first over a horizon, just like our light did. The visual floor comprises miles of waves, but the compression rate is such that the waves at 0.25 miles or so are already very near the horizon. The camera horizon at a 6-foot height is going to be 3 miles, assuming a 1 arc minute. So objects greater than 6 foot high will set at 3 miles unless the resolution improves, and we're going to have another horizon gap. If the flashlight were a ship, the same effect occurs. So again, the red orthogonal lines are nearly horizontal, as the horizon and the visible floor is going to be 50% of the lower visual field. We just got higher. And we can turn to another floor example within a Walmart here and imagine the walls and the roof were removed, leaving us just the sky above. And it would look something like this. And we can now stand up and imagine the floor comprises several rows of crops. And we get back to this. We just stood up like we did in the hallway. So the flashlight now becomes a tractor, let's say, and it disappears bottom first over a horizon. This isn't the curve of Earth, it's how vision works. So here's where we're at as far as a recap. We've discussed things getting smaller with distance, small things disappearing, and small things disappearing with distance secondary to the vanishing point and setting objects. Now we're going to cover small obstructions within perspective very briefly and some upward refraction issues. So now we're at secondary to small obstructions within perspective. So within our floor example here, the last 3 golf balls are all on the same horizon line, and they no longer ascend within perspective. The floor tiles are a bit uneven in this case, and if there were an obstruction nearby, say 7 feet away, it would obscure the image further away at 130 feet. If we are beyond the horizon line at 95 feet in this example, we have lost a height equal to d tan theta, or 130 feet times the tangent of 1 arc minute, or 0.55 inches. The golf balls have a diameter of 1.6 inches, so our golf ball is reduced to 1.6 inches minus 0.5 equal to 1.13 inches. Again, given an obstruction, or given the amount of set. So because perspective ascends quickly and then tapers, an obstruction nearby would completely obscure the bottom of an object far away. Using similar triangles, and assuming we are at the portion of vision where this perspective plateau occurs, again, typically beyond 20 feet or so, we see that if there were an obstruction 30 feet away, near that second golf ball, or just 6 millimeters above the eye line, it would be enough to obscure the entire golf ball 130 feet away. So we can have summarized this effect by stating small obstructions in the foreground obstruct distant objects. So if that doesn't make sense, maybe it will here if I explain the diagram. So the red line from the eye to the purple line is again going to have a rapid ascent rate, an exponential ascent rate. And so we know that objects, even though they encroach upon that purple line, they don't actually start to set for quite a bit distance away. So that means that there's essentially a plateau or a table of an area or distance across which an obstruction along that point would completely obscure the object further down the road because its angular size is going to get smaller. And so we calculated that for the amount of the golf ball that would be missing at 130 feet, just from diffraction, we would get roughly 0.13 inches of loss. And so, or excuse me, 0.55 inches of loss, and that would give us about a golf ball roughly 1.13 inches tall. And so that's why I've cut off the bottom of the golf ball in the diagram. So that's what we're looking at. And so in the bottom right hand picture, I've kind of pointed to that golf ball that is 130 feet away. And so if we were to put an obstruction, let's say this blue triangle, and we were to put it in the nearby vision, let's say at 30 feet away, and I've kind of put that there on the lower right, I put the little blue triangle next to the 30-foot ball. But you can see how if I were to put that in line with the 130-foot golf ball, it would completely obscure that ball. And we can calculate that ratio or what height would be required to obscure that distant object by just using similar triangles. And so that's what I've done with that formula, solving for x. So in this case, X is 6 millimeters. So a 6 millimeter obstruction above the purple line completely obscures the entire golf ball 130 feet away. And so for the 1 centimeter, and this is for the 1 centimeter observer height, so an obstruction of just 3 millimeters would obscure the entire bottom half of that golf ball. We would lose the bottom half of the golf ball. So keep in mind too from our formula before that for the 1 foot observer height, knowing that 0.05% is taken up within the lower 1/4 of vision, only 1.56 inches is going to be within that lower 1/4 of the visual field. And when we lowered our height down to 1 centimeter, again, 0.6 inches takes up 1/4 of the image. And I also want you to note here again how when we had a 1 foot observer height, the red orthogonal lines where the corners met extended off into a distance roughly 2,600 feet away. But as we lowered our eye height, that vanishing point essentially became a vanishing line and merged into that purple line we see that is much nearer to us. So here's some practical examples. So given a 0.4 inch observer height with the 1 arc minute of resolution, what height of an obstruction 60 feet away would obscure 0.4 inches of light at the end of a hallway 360 feet away? So it's just the same thing. Now I'm using a flashlight and an obstruction instead of a golf ball and an obstruction. And so we find that just 1.7 millimeters would block the entire light 360 feet away. Same thing here. Now if I just stand up and I'm going to extend this to a further distance, given a 6 foot observer height with 1 arc minute of resolution, how big would a wave have to be 0.25 miles away to obstruct a 250 foot tall cruise ship 20 miles away? So it's the same relationship, 250 feet of cruise ship 20 miles away versus X amount of obstruction a 1/4 mile away, and you would get a wave of 3 feet. So a 3 foot wave just a 1/4 mile away that has encroached upon that purple line already because of the rapid ascent rate will obstruct the entire boat to 20 miles away. And a 1.5 foot wave, very reasonable, especially with choppy waters, would obstruct the lower half of that boat. So that's small obstructions within perspective. Now we're going to cover upward refraction of light. So some of this was contained in part 4 of the series. I encourage you to watch that for greater detail. I'm not going to go over all of this again, but just to summarize the basic rules of it all. So refraction is secondary to light passing through different densities or indices of refraction. Formulas for the indices of refraction, which are Edlin, Sidor, Peck, Jones, etc., reduced to pressure divided by temperature with some additional variables for CO2 and humidity. But by and large, when temperature rises and pressure diminishes, which is an emission, the index of refraction goes down and light bends up. By and far, by the way, temperature is the largest factor for refraction. And this occurs commonly over water, and the apparent image is brought lower than the actual image when there is an emission phenomenon. In other words, when there is a warmer layer above the water because of the specific heat of water typically giving off heat during the day and absorbing during the night, when it's giving off heat during the day, many times you will observe upward refraction across water, and your eye straightens that image out to create straight lines or assume straight lines, and so you bring that image down. And so that's diagrammed here below, and please see part 4 for a greater description of this effect, and for some of the people who are doing great observations out there that allowed me to extrapolate kind of what was going on. And the same effect occurs for the bending of objects with distance, and again, please see part 4 to go over that. But I'll just kind of roughly cover it one more or in a different way here. So for these Lake Pontchartrain power lines, which are photos from I-10, one can find the true horizon line by using orthogonal line convergence toward the vanishing point. So you can use all these towers to find where the similar points within the towers create a horizontal line, and that is the observer's horizontal vanishing line. So if you were to take the top aspect of the towers and draw lines through the same point and off into the distance, you would have one orthogonal line. If you were to do the same thing along the bottom part of the tower, you'd have another orthogonal line. And this creates essentially a fan shape as you move up and down this tower. But there will be a certain point along the tower, which is this lower apex of that triangle that's kind of at the near that purple line, where there is a straight line between all the points within the towers, and that is your horizontal vanishing line. So in all these pictures, the apparent horizon line is lower than the true horizon. In other words, the point where the purple line is we're going to assume is our true horizon. It's the horizontal vanishing line or horizontal orthogonal line. But we see that the apparent horizon, which is that water line, is lower than that point when we see greater amounts of bend. So the greater the bend, the lower the apparent horizon. And this makes implicit sense because that is a phenomenon of upward refraction over water. So again, please see part 4 for more discussion on that particular topic, or that aspect at least of the topic. But I wanted to kind of speculate here, and this is just speculation, but if upward refraction is a normal, common, everyday phenomenon, such as fairly constant emission from Earth, up into the atmosphere, as opposed to absorption, sunsets may occur partly because of a personal atmospheric dome where it descends through the dome or curve sooner than perspective would dictate, and would therefore not reduce in angular size to an appreciable amount. So again, complete speculation on my part, just providing a possible mechanism whereby this would occur. So if we take our bridge example and we just flip it and invert it to what would be happening if we were lower down. So in the bridge example, we're higher up observing this bend. Now we're going to be observing something above us, but also subject to upward refraction. We would get something within perspective that looks something like that blue funnel shape going down. The bridge would descend at a quicker rate within perspective, and those transversal lines would diminish in angular size, but they would do so at a lesser rate than perspective would dictate. So if we replace that bridge with essentially the sun and were to model how that would descend within perspective sooner than perspective would dictate, we would get a similar phenomenon. So the distance to the sun changes little within that scenario because it rotates within our vision on an arc relative to the observer instead of traversing away from us. So since the distance changes little, the angular size would also change little. And so please see, I left a link for a possible model of how this may occur for observations. And you can play around with that and move the or mess with equatorial positions and star positions and so forth with a personal dome effect. So, and all the positions of the stars and the sun work out the same way as they do on the heliocentric model. So now we're going to cover something different within this upward refraction phenomenon. This is going to be the inferior mirage. So within the differentially compressed lower half of vision, an apparent horizon line will form sooner than expected from an abrupt angle change, such that theta refracted becomes theta reflected once theta critical is met. So again, please see part 4 for more discussion on that. This is called a total internal reflection. So when this occurs, the mirror layer reflects the objects above the eye line, most commonly the sky or the distant landscape, until the true horizon line is met in the distance. In other words, the inferior mirage creates an apparent horizon that is lower than the true horizon and very close and nearby. So it's very important to understand this concept of perspective when you're looking at this when you're mapping an orthographic view into perspective. So when I take the image on the upper left and I am a 6-foot observer standing above those waves and I have a certain eye line and I'm looking at those waves, when I rotate that into perspective, that purple line is going to be encroached uh, by those waves. In other words, I don't see that observer gap that is present there. I just see the waves that are off in the distance at the same purple line. So if I were to replace, or if I were to place a emission zone, an upward refraction zone, a less dense, less optically dense zone between the purple line and the waves, such as an emission occurrence, right? And these boats that I have within that frame are going to move off into the distance, okay? Then I would see them start to ascend within a mirror line or within this mirror zone, but that they're still in the water. Okay, they have not met the true horizon line, which is that purple line, after which they would set. Instead, what ends up happening is they get enveloped. They get essentially um, uh, encompassed by this dirty air, we can call it, to take Anthony Riley's term. And what ends up happening is they create false mirrors or mirror points, uh, beyond the apparent waterline. And it gets further and further up the boat. But none of those lines are the actual true horizon, which is much further away and much higher within the frame. So if you were to remove this mirror zone and you were to watch this boat move away from you, you would just be observing water. There would just be water in place of this, of the mirror zone. So again, the upper left perspective, 1-point perspective view is what you would see without the mirror zone. And the green kind of rectangular emission zone, that's when you would see that inferior mirage take its place of that distant water. But it's just water. So if you were to shine a light, let's say, from that boat, before that boat had met the purple line, you might still be able to see it, kind of breach through that air. But once that boat has been set beyond the purple line, the true horizon line, nothing will ever bring it back. You will never be able to see through that point because that's water. So hopefully that makes sense. That boat has set into that horizon gap beyond your lower horizon limit. You cannot bring anything back once it's gone after that point. You might be able to still see an object if it's within the mirror zone prior to that distant point, prior to the purple line. But once it's risen above that purple line and started to set, you cannot bring anything back. So no matter amount of zoom or anything. Now, if you change observer types to a different aperture, okay, and you magnify the object that way, say with a telescope or something like that, then you conceivably would be able to bring it back because you have a lower resolution limit. So hopefully that makes sense. When you're looking at a photograph with an inferior mirage and you're looking at the apparent water line, the actual point where the mirage starts, that is a nearby point, okay? What I've noticed, looking at many of these inferior mirage photos is that the mirror zone is a very small, when you're zoomed out anyway, it's very small within the frame. And it seems to occur within that 128 to 256 compression rate up to the purple line. So the apparent water line, if we're doing that from a 6-foot observer, that's only that's less than a mile away. So again, the apparent water line is actually very close. It's not the true horizon line. So, which would be another 2 miles beyond that point, at 3 miles. So lastly, I want to provide a possible standard upward refraction calculator. And again, this is the assumption that 7/6R was taken off of actual observations of a loss rate, but that they assumed improperly that downward refraction was occurring, which is extremely rare. in my experience, and upward refraction is by far the more common phenomenon, which is emission from bodies of water, such that it is slightly warmer above the water than it is as you go up in altitude. So assuming theta is met along the lower visual field, okay, so assuming that we've actually encroached the diffraction limit to some extent, and the object being viewed is beyond the observer horizon distance, so again, you're actually beyond, the object is beyond the diffraction limit, we can quantify a standard amount of upward refraction for the remaining aspects of that object as follows. So in other words, we have something that is setting in the distance. So how much loss can we extrapolate from that? So if we assume standard terrestrial refraction is misinterpreted across warm surfaces as 7/6R, more commonly 14% or 16% less the curvature of Earth, we can use the rough approximation of 8 inches per mile squared as an approximation for Earth curvature if the observation is less than 100 miles to formulate a drop rate for the remaining aspects of the objects above the eye line. Please, you can see part 5 for the derivation of that 100-mile point. But we will assume that this standard refraction rate has overlooked the observer height loss from the observer equal to essentially from diffraction loss, and that it was incorporated in the 7/6R refraction rate. In other words, that they to solve for 7/6R to find this 16% refraction rate, they did not subtract out the diffraction loss. We're going to assume that they included it. Therefore, the disappearance rate becomes the observer height plus the reversal of standard 14% or 16% R terrestrial refraction as upward emission refraction. So if we lessen our curvature rate of 8 inches per mile squared by 14%, or 14 to 16%, we obtain 6.9 inches per mile squared, or roughly 0.55 feet per mile squared. This curvature formula, however, has an overestimate if the observer has any height, and the formula is often split across the observer height and the object height as if one were looking down across a bulge. This is how Earth curve calculators work. So I've provided a crude estimate for how that works with the diagram down on the bottom. That's the curvature model assumed within standard terrestrial refraction at 0.55 feet per mile squared divided by 2 if the observer and the object are the same height. Again, that you are looking down across a bulge. That is what a Earth curve calculator assumes. And we're going to reverse that phenomenon and instead bend the light across a flat surface, which is what I depicted to the right of that picture. So again, if we assume this assumption was factored into the estimate for the Earth's curvature, we can divide 0.55 feet per mile squared by 2 to get 0.277 feet per mile squared, and remove our observer height if the object's height is more than or equal to the eye line or the observer height. Essentially, I can remove it as a factor, as long as the two points across the bulge are going to be of roughly equal height. So when comparing this rate of to diffraction loss, we see that this 0.277 feet per mile squared, we see that this rate underrepresents the loss until approximately 7 miles, or 13 to 14 feet of loss. So we need to be viewing an object greater than 7 miles away in order for this to be a factor. And this also assumes that light reaching our eye for every foot of observer height will curve at this rate. In other words, for a 6-foot observer height, I am viewing the curvature of rays from 6-foot portions of the object in the distance, so that I can have it divided by 2. If the observer height is 100 feet, I am viewing 100-foot portions of the object being refracted at this rate. The overall effect is that the object is still dropped as a whole, but in those portions. The height of this effect is unknown, and light may predominantly refract upward as long as temperature diminishes with altitude. So if we're within 1 kilometer above sea level and observing an object greater than 7 miles away, our formula for the loss rate of the remaining aspects of the image above the eye line is 0.277 feet per the mile squared, or loss equal to 0.277 feet times the distance squared, where d is in miles. So examples below, which are in the next slides, will assume theta is 0.02 degrees, and it has been factored into 7.6R. Again, these are assumptions, but what the assumptions provide is an accurate calculator, as will be seen. So again, this is for if we had a clock tower 3 times the height of the man is 6 foot, we would still have the same curvature rate of the light rays, and you would reduce that object by the same amount, even though you have differing heights. So let's take some examples here. So the first one is Jose J.G. Gonzales. Video link is in the description. We have the possible loss for the Lighthouse in Kemah, Texas, which is 150 foot tall lighthouse as viewed across 17.5 miles of water, when he had roughly a observer height, which again is going to be negligible according to the derivation of the formula, of 22 feet. And so when we plug in, we find that for this particular instance, we are going to be missing roughly 84 feet, which almost exactly corresponds to the amount when we do a blink test. But again, a blink test is an erroneous assumption because you can already see that the lighthouse is differentially expanded. And again, the differential expansion is due to upward refraction phenomenon, as discussed in part 4. Let's do a second example. This is from Gary is Right. Possible loss of the CN Tower, Toronto, 1,800 feet tall, as viewed across 31.5 miles of water, with again a negligible observer height of 15 feet. We're still going to plug in and get 0.277 times 31.5 feet or miles squared for 275 feet missing. The Rogers Center is 282 feet tall, and we are missing roughly the Rogers Center's worth of information if we were to apply a blink test, which is once again a false way of trying to compare sizes, because we do have some aspects of differential compression and expansion within a field, but it does provide a calculation for the amount that we are potentially pressing this image down into the distance. Another example, possible loss for Blackpool Tower in Blackpool, England, 518 feet tall as viewed across 30.9 miles of water with roughly 60 foot observer height. Again, same thing, 0.277 times 30.9 miles squared gives us 264 feet missing, or roughly half of Blackpool Tower. And that's from Dazzathecameraman. Another one from Joshua Nowicki, possible loss for the Willis Tower, 1,700 feet as viewed across 55 miles of water with a 10 foot observer height. In this case, we're going to get a loss of 837 feet, which is roughly where that red line corresponds to along the photograph, knowing that the 311 South Whackers skyrise is 961 feet tall. And finally, this example, which has been talked about recently, so this is from Conspiracy Cats. Why is Mount Rainier smaller than Mount St. Helens when it is twice as far and twice as big? So to find out why, we first need to return to our perspective diagrams to see what should happen within perspective. So I'm going to take our buildings here, just like we had in our hallway, and I'm going to I want you to pay attention to the gray and the yellow blocks in this case, or we'll call them the yellow and the gray building or object of any kind within perspective. How does it change when we reduce our height? Okay, so I'm going to reduce our height now. There's one iteration. Here's another iteration. So how did they reduce? Well, we can pull them out and look at them. So all blocks have the same orthographic size when we view them from a side view. But in perspective, the yellow block is half the angular size as the gray one because it is twice as far away. Again, noting that we double the distance, we half the size. Similarly, if the yellow block is twice as far away and twice as big orthographically, it would exhibit the same angular size as the gray block. So in that case, within perspective, they would be the same size. So note that the observer position changes the position of the yellow block relative to the gray one. the lower the observer height, the steeper the descent rate of that yellow compared to the gray. So if I were to, in this case on the lower left, have the yellow and the gray block be the same size orthographically, then within perspective, the yellow block is going to be half the angular size if it is twice as far away. However, if the yellow block is now twice as big as the gray one orthographically, or let's say in real measurement, in real terms, then within perspective, we see a slightly different phenomenon. The descent rate is still the same, but we see that at a certain point, their heights become equal when we reach the floor. In other words, when our observer height gets down to where both bases are roughly at the same level, within perspective, we see that their heights within perspective would be the same. So again, since we have our height and distance relationship as talked about, we would expect Mount St. Helens and Mount Rainier to be roughly the same angular size when we reduced our height down to the base. Their height differences are a function of observer position, but their angular size is a function of distance. In other words, how big or how tall Mount Rainier is in comparison to Mount St. Helens is a function of a couple things. One is the distance away from the observer, and another is the observer position in relative to the mountains. So if I get higher up, right, I'm going to be seeing much more of Mount Rainier, and Mount St. Helens is going to kind of shrink down. That's just, again, that's a function of perspective. But when I get lower down, does Mount Rainier ever get to the point where it should reduce below Mount St. Helens? And I would argue no, it does not. Once you get down to the ground level of Mount St. Helens, Mount Rainier is twice as big and twice as far away, so its peak will be roughly the same height as Mount St. Helens. And so you can see that their angular size is roughly the same. The two mountains are roughly the same angular size but Mount Rainier is twice as big and it's also twice as far away. So we extrapolated our gray and yellow blocks out. So if the yellow block were twice as large as the gray one, it would be the same angular size and twice as far away. And if I just put some mountains within the gray and yellow block and I reduce my observer height, we can see that once we get down to the base level, that their peaks should be roughly the same size or the same height. But that before that, Mount Rainier should have a taller or a higher peak within the frame than Mount St. Helens. So the higher the elevation, the higher the yellow brick will be in comparison to the gray one. But once we reduce our elevation to sea level, i.e. the floor, without diffraction or refraction loss, or reducing our distance to the mountain, we cannot bring the yellow block lower than the gray one. So since diffraction loss between Mount Rainier and Mount St. Helens accounts for a difference of only 91 feet, such that d10 theta equal to 104, 104 miles times the tangent of 0.02 equal to 191 feet for Mount Rainier, minus the Mount St. Helens loss, which would be 54 miles times the tangent of 1 arc minute of 100 feet. So that gives us 191 feet minus 100 feet, that's 91 feet. So because that difference is essentially very low, in other words, Mount Rainier could possibly be 91 feet lower than Mount St. Helens, but 91 feet is negligible. So we should examine if refraction can account for this observation. So we're missing approximately 1/4 of Mount Rainier, and within that photograph you can see how short Mount Rainier is. And there is a large body of water between the two peaks. If upward refraction were occurring, or emission occurring over that lake and in the surrounding air, we may be receiving light curving upward to the observer from that distant peak. So the possible loss for Mount Rainier from Council Crest Park, Oregon, which is at 1,000-foot elevation, as viewed 104 miles away, would be 0.277 times feet per the mile squared, or 2,996 feet missing, assuming upward refraction. And we can see the lake. If we do the Google map, we can see the body of water there between the two peaks. So assuming they are supposed to be roughly the same size in the photo, we see that Mount Rainier is shorter by approximately 1,858 feet. Again, Mount St. Helens is 8,363 feet, and Mount Rainier appears to be at 6,505 feet when compared to a side peak, which is what's demonstrated in the photograph. So 1,858 feet at 54 miles translates to roughly 3,585 feet at 104 miles. In other words, the amount of loss translated twice the distance out. Again, just like triangles. 1,858 divided by 54 equal to x divided by 104. So for a 14,000 foot mountain, given that there are several still likely unknowns at play here, we are at about a 500 foot difference between these observations. But for a 14,000 foot mountain, I would say that's pretty close. So assuming standard 16% upward refraction of light across a flat plane on this particular day, we get 2,996 feet of expected versus about 3,585 feet of what we can possibly see within the photo. Again, noting that there are possibly several other factors at play. So greater refraction accounts for the loss, such that 0.277 feet times the distance in the mile squared would yield a refraction rate of 0.31 or 0.331 feet per the mile squared. In other words, light is possibly bending to a higher degree within these particular conditions on this particular day within this particular elevation on this photograph, such that it was bending at a slightly higher rate than what standard would be assumed. So its bending rate is 0.331 feet per the mile squared. So just for a recap, again, a concept for vision that things get smaller with distance, small things disappear, and small things disappear with distance secondary to the compression rate within a given field of view, with the subpoints of vanishing points and setting objects in the horizon gap, small obstructions within perspective, and upward refraction of light. And we gave examples of the inferior mirage, compression and expansion effects, and a standard refraction rate. So hopefully, I know it's a difficult subject, but thank you for the attention, and God bless you all, as always.